Welcome to the another video of the power quality. In this video, we will be solving this problem. A single phase AC voltage controller. Alright, single phase AC voltage controller is fed to a heating load and which is a purely resistive load of 10 ohms. So let me draw that circuit for a single phase AC voltage controller. AC voltage controller is nothing but thyristor back to back connected, so that helps to control the AC voltage both in the positive half and the negative half. So the thyristor here back to back connected, it is connected with a resistive load of 10 ohm, and now the feeder that is there connected with it, and this feeder is having a resistance of 0.1 ohm each. So this is of 0.1 ohms, and the feeder is there. The feeder in and out, the both is having a nearly a resistance of 0.1, and the load is of 10 ohm, and the supply that is being given to it is through a AC voltage. The AC voltage is having a voltage of 220 volts, 50 hertz, and the value of alpha is 120 degree, that is its fibs. Now as per this question, let us draw the output voltage and input voltage waveform. So now if I draw the output voltage here, let us say the input voltage Vs and the output voltage is, let us say, VL. So let me draw the input voltage first by the dotted line, and that's what the input voltage looks, sinusoidal voltage, with x-axis is omega t, and this side is pi and 2 pi. So obviously this 90 and this side will be 120 degrees, and your 270 and this will be 300 degrees. So it is said that alpha is equals to 120 degree. So at 120 degree you will have the output voltage will be reflected after 120 degree. It will follow same the input voltage. So this will be the output voltage that you will be getting in the output. So in the output, if I just draw the output voltage here like VL, so you will be getting the output voltage like this up to pi, and from here you will be getting like this up to 2 pi. So like this you will be getting a output voltage between this is the pattern of output voltage you will get, and Vs is and VL will be in this direction. It will look like this. And since it is a resistive load, the current waveform will be the same as the voltage waveform. So obviously the current will be the same as the voltage waveform, and this will be the value. This is what the IL. Now if the current is over IL and this current is IS, so obviously this like IL is equal to IS. Anyway, if I calculate the RMS voltage, I can get what is the RMS current. So let us find, the question is asked that AC source RMS current is asked. So to get the value of RMS current, we need to find out the RMS voltage. So let us find out the RMS voltage in another slide here. So the formula of RMS voltage, let me write. RMS voltage square is equal to 1 by 2 pi integration of 0 to 2 pi V square theta d theta. That's this is the formula. So for this particular case, the VRMS square is equal to it is like symmetrical, so we can just take 2 by 2 pi and 0 to pi. Instead of 0 to pi we can write alpha to pi taking this value as alpha equals to 120 degree. So let us take it from alpha to pi and pi plus alpha to pi. Let us do this in this way. So here we get alpha to pi as, and this v square, it will be Vm square sine square theta d theta. So that is nothing but Vm square by pi. Sine square theta will be 1 minus cos 2 theta divided by 2. Take this 2 out. 0 alpha 2 pi and d theta. So this will give us Vm square by 2 pi. Integration of 1 is theta and sine cos 2 theta is sine 2 theta by 2. Limit from alpha to pi. And this will give Vm square by 2 pi minus alpha. This will be minus of sine 2 theta, so sine 2 pi will be 0 and alpha will be there, so minus minus plus sine 2 alpha by 2. So this is the RMS value, Vrms square. So let us put the values here. The value of alpha is 120 degree. So in degrees, so we can convert into 120 by 180 into pi, that is 6362, 0 cancel. So 2 pi by 3. So we can put the value of alpha 2 pi by 3 and evaluate this. So this is coming around 9462.253. So that is nothing but Vrms square, and we can get out of this Vrms will be equals to square root of this answer, that is 97.274 volts. So that's the RMS voltage that we have obtained for this waveform. So here the Vrms value is 97.274 volts. And if I want to calculate what is IRMS, or in short I can write this as IL, I will write down this as Vrms divided by R effective, that is equal to 97.274 divided by R effective is the total resistance in the path, that is 10.2 or 10 plus 0.2. So this will be equals to 9.5366 amperes. So that is the value of the IL here. So obviously the IS is the same value. So another question is that loss in the distribution system. So this IS is also the same as IL. So we can say the losses in the distribution system is IS square into R. So the losses in distribution system is IS square into R, and that will be which the value of R is R of feeder. So it is 9.5366 square into 0.2, that will be equals to 18.189 watt. So this is the power loss in the distribution system, 18.189 watt. Now if an ideal shunt compensator is used to compensate power factor to unity of this load, like somewhere this load current is not having a unity power factor, but if there is a compensator which can make this load as a unity power factor, then what will be the AC source RMS current, that what will be the current in that particular case. So in that case we have the power which is required by the load is I square, like this is what is required, IL square into R L. This is the power which is required, this is the active power, and for which we will be dividing this, instead of the voltage over here VL, rather we will be getting the VS. If we use a compensator, then this is a 220 volts. So this will give you the value of IS after compensation, ISC, or IS after compensation. You will be getting this value. So that value will be equals to IL square, that is 9.5366 square, into RL. RL is the effective value is 10, whatever is consumed by the load, what is the load resistance, 10 divided by 220, and that gives us the value equals to 4.1339, that much ampere. If the value of ISC will be 4.139 ampere, then now the new loss that will be there in the distribution system is obviously is equal to ISC squared into R feeder. That will be equals to just square of this value, 4.1339 square into R feeder is 0.2, the resistance of the feeder. So this value will be equals to 3.417 watt. So you will be getting the losses here because before compensation it is 18.189 watt, and after compensation it is 3.417 watt. If you take the ratio of the distribution system without and with compensator, so without compensator it is 18.189 and with compensator it is 3.417. If you take the ratio of these two, it will be coming around 5.32. So it is like we are, by using a compensator we can reduce the loss by 5 times, or without the compensation the losses is 5 times more than with compensation. So that's the ratio of the losses in distribution system without and with compensator. So thus in this video we learn about how to evaluate the RMS value of the output current in a single phase AC to AC voltage controller, and then we get what is the current, RMS value of the current IL, and if we use a compensator then we will be dividing this active power of the current, will be dividing this entire load, whatever load required, divided by the 220 volts, and that will give us the value of current is 4.1339 ampere. And if we have the current like this, like 4.1339 is sufficient to give the load. Before compensation the current is 9.5366 ampere, but after compensation the current is 4.1339 ampere, and what we are saving is the losses in the feeder, which is reduced by 5 times. So this is what we learn in this video. Thank you very much. In the coming videos we will be getting another few important problems. Thank you.